Yeah, I think we can start again. And thanks, Martino. Let's go.
All right. Everything is fine. All right. So welcome to the second session of today. That's going to be very similar to the clustering tutorial, but this time we are going to look into two different aspects of machine learning. Part of two different families again of the various models, right? So let's look into this again. We are going to look into dimensionality reduction, which is this area, and classification, which is this area. I put them together not because there is any reason why they should be together, but because time required that I had two sessions, and also because I'm going to use the same data set for both. Then the last thing that will be missing is from this specific sort of chart is the regression part, which will be covered by Claudia in the afternoon together with the model selection part. And then we will have covered, a tiny amount, a few examples from all the big families of machine learning, except deep learning. If you have any problems hearing or seeing me, please let me know. And Thomas, feel free to interrupt me if there are comments of that kind, because it's the most important thing. Okay, so I'm going to close this. There is a digit and dimensionality reduction classification notebook. So if you fall behind, you can always go and look at that one. But again, I would recommend you don't use it right now. It's always nicer if you type and follow along as I do. So I am actually going to use a completely empty new notebook. And the first thing that I will do is introducing the data set we are going to use. That's called the digits data set. Digits. So there's a data set called enlist handwritten digits, which is the one that I showed you earlier. That's really one of the most common benchmarks. Benchmarks means it's used to test models and to see how effective they are. So it's very famous in the machine learning community because it's really used as an example whenever you're testing new models, whenever you're trying out and doing research on machine learning among the easy data sets. What we use today is an even smaller data set, which is the one that is included in scikit-learn. Scikit-learn has example data set. And if you want to learn more about machine learning, somebody was asking during the coffee break, how do we learn more about machine learning? So one nice way is looking at these scikit-learn.datasets sub-module, which contains a lot of example datasets. And typically for each of these datasets, the scikit-learn documentation has a tutorial as well. So you can try experimenting the various models that are in scikit-learn and using them on the various datasets. Each dataset is usually very small and is designed to be a good example for one specific kind of task. For example, there are things like predicting the house prices of Boston based on things like location, size of the flat, number of rooms, and things like that. There is predicting whether the various people who are on Titanic, you can predict whether each person is likely to die or not in the accident of Titanic based on in which class they were, which part of the ship they were located, and all these things. There's the iris flowers datasets, which is a clustering example. So telling the different species of iris flowers based on the sepal and width and length, and the petal width and length. And then there's digits. So that's the one that I'm going to present today. Import load digits. And then digits equals load digits. It's a function that reads up the files. Okay, so now we have an object called digits, which is it's sort of a dictionary. Of course, during the coffee break, there was no noise, no hammering. Now that I restarted, they start again. So, okay, so we can, every data set, again, scikit-learn has this very standard way of looking at things. Every model has the same syntax. Every dataset also has the same syntax. So when you've learned how to use one, you've learned how to use them all from the coding perspective. From the theoretical perspective of how a model works, which hyperparameters we should choose, and all these things, remember that you have to study yourself. So digits, it will have a key called description. If you print it, it will nicely tell you a lot of things. So it tells you how many things there are in the dataset, what's the number of attributes, which is what I also call features for each of these. What are they? They are pixels of the various digits, and they go from 0 to 16. So 0 is white, 16 is black, and there's a grayscale in between. And then it tells you who made this dataset, where it comes from, and so on and so on. So we have a bit of information. So let's look into it. Remember, define the task, find the data, display the data, pre-process the data. Display the data is figuring out how this data looks like. So to be more brief, digits, data, and labels equals digits labels, so we don't have to type it every time. And then let's have a look. Oops, sorry, it's actually target. That's the syntax that we use. So let's look at the data. Print data.shape. This tells us how many data points there are and how many features per data point. So there are 1,797 data points and 64 features, each of which is a pixel. How about the labels? Labels.shape, as you can imagine, is going to be just 1,797. And what are they? How do they look like? Each of these labels is a number from 0 to 9, which corresponds literally to number 0, number 1, like digit 0, digit 1, digit 2, digit 2. So it's telling us what is the number in the image. Okay, I also would like to display how these look like. So let's use matplotlib. And I use the function called imshow, so that shows an image. So let's look into the first data point. So there are 1,797. We look at the first one of those. Sorry, something is happening here. Okay, we have to reshape it because we have 64 digits. So 64 features, which are pixels, but it's actually 8 by 8. So we reshape it to 8 by 8. Oof. And we also want this to be plotted in grayscale. Okay. So that's how it looks like. That's a 0. Why there are 2 8s in the labels? So these are the label. These labels are all the labels for each data point. So this is labels.shape 1,797. So that's the, sorry, I'm answering a question for context. I read the question in the slide. There are 1,797 of these. So that's for each of these images. What is the label? So of course they are repeated because it's one per sample. So here you go. So that's a 0. I think we can see that it's a 0. And the label that we see here, we can also plot the corresponding label. So that's going to be labels 0, and that's 0. I can also plot another one. Let's plot number 10. That's a 0 again. So for a change, let's plot number 100. That seems to be a 4. So if I plot the 100th label, that in fact says 4. So that's good. All right. So now we have to use this data set. And as I said, we are going to use it for two things. The first thing that I want to look at is dimensionality reduction. This is the side of machine learning that I've talked about the least so far. I didn't really give you examples of this in the introduction. Maybe I should have. What's the idea of dimensionality reduction? Well, as I said many times, there are 64 pixels in here. So we have a 64-dimensional data set. This is already a relatively small, like low number of dimensions. Because if you think about an image that is 1,000 pixels by 1,000 pixels, like a photograph, 1 megapixel, 10 megapixels, that means 1 million per million data points. Sorry, not data points, 1 million features, or 10 million features. So 64 is kind of low. Now think about this. Each of these images, you are physicists and mathematicians, so I think you will be able to do this. Each of these images lives in a 64-dimensional space, okay, where each dimension describes the value of a pixel. And we cannot visualize this 64-dimensional space. It's too large. And it would be even worse if we had a 1,000-dimensional space. However, you can imagine, again, as physicists or mathematicians, you can imagine that, in fact, the whole data set lives in a subspace of this data set. It's not that you have all the possible combinations of pixels, okay? So you are not really filling in all the possible directions of the 64-dimensional space. Because, for example, this pixel here is going to be usually white, for example. So, and then there will be correlations. So if this is black, normally this is also black. So the direction where those are different is going to be not well populated. It will happen rarely. Okay, so we are actually talking about a relatively small subspace of the 64-dimensional space that is important. I'm talking abstractly, but I assume that you're used to it. If not, it doesn't matter. We will also find other intuitive ways of talking about this in the course of this tutorial. Okay, so how do we find this subspace? We may want to do this for two reasons, and I will go over these two reasons many times. One reason is we want to visualize the data. We want to have a look at it at a glance. Like earlier today, I was telling you it's very difficult with 3 dimensions. You weren't able to see that it was clustering properly. Okay, so that's one aspect. I want to plot it, and I want to plot it in a relatively sound way. So I just want to look around, find some structure. So I want to make it 2-dimensional, or 3-dimensional or something. The other possibility is I want to find the right. I want to find meaningful dimensions. And this is a bit more tricky to understand intuitively. But finding this subspace where the data lives of the 64-dimensional space, finding the smaller subspace where the data lives can tell us something about these correlations that I was talking about, the absence of black in this corner. It can tell us about what is the typical variability. I will be more intuitive and give more concrete examples about this in a moment. So for this job of, we have algorithms called dimensionality reduction algorithms. So we use these for visualizing and for finding relevant combinations of features that may have a semantic meaning or a useful meaning for us. I will, as I did earlier, I will first do it with scikit-learn, and then I will explain what I've done, what is behind the algorithm, and how we can interpret the result. I want to show you the juicy part of the code first. So from scikit-learn dot decomposition, import PCA. PCA means, I'm going to write it in a comment, principal component analysis. So this tells you that we are doing dimensionality reduction in the sense that we are finding the principal components. The principal components are those directions that I was mentioning that are relevant, that are that are more interesting because they describe the variability of our data set more than the others. Okay, so let's try PCA. The model here is PCA, and I want the reduction to happen toward 2 components. So we go from 64 to 2. Okay, and then I do model.fit. That's the thing that I was doing earlier, right? For clustering, I did model.fit. In this case, I don't only want to fit, I also want to transform the data. So I also want to do the prediction and the embedding into the lower dimensional space at the same time. So there's a function called fit transform that does both things at the same time. Data is our data that I defined here. So it's the digits and it's samples, comma, features. So again, as earlier today, always the same in scikit-learn. You have on the rows, you have the samples, and on the columns, you have the features, which here are the pixels. So the result of this operation is going to be my transform data. Okay, it has converged very quickly. Let's plot it. Okay, so these are the first 2 principal components. That's how they're called. It finds the principal component, and we get 2 of them. This is the first principal component, and this is the second principal component. Okay, and I'm going to use small dot size. This is how it looks like. So what are these things on the x-axis and on the y-axis? For now, I haven't explained what PCA actually does, so you don't know, but I can tell you that these are linear combinations of the pixel values. So we found a linear subspace of our 64-dimensional space, and we've applied this linear transformation, a projector, in fact, if you want to speak mathematically, a projector that projects to this 2-dimensional space. And these are the 2 directions, the 2 basis vectors that I've chosen on this 2-dimensional space, which are called the first principal component and the second principal component. You can also work on with a larger number of components, and then you have the 3rd, the 4th, 5th, and in fact, until the 64th. And I will explain later why you can also do a dimensionality reduction that doesn't, in fact, reduce at all. Okay, so this doesn't look particularly interesting. It does look a bit more interesting if I actually plot the labels as color here. And then I will see that the structure starts to emerge. But because I don't want you to just listen all the time without doing anything, I want you to do some work. I'll let you do this. So please change the plot to show labels as colors. Okay, let's spend a couple of minutes doing this. So what's happening? So I wanted go ahead and do it. In the meantime, maybe I will keep chatting and answering some questions. The first point that I want to make while you're doing this is unsupervised learning, right? We have not used the labels. When I did fit transform here, I passed the data, but I did not pass the labels. So the model doesn't know anything about the labels. So that's unsupervised learning. So if the labels, if we see a structure in the labels here, that means that the dimensionality reduction was successful, that it did something nice. Somebody in the Slack comments witchcraft. So I accept it as a criticism of the fact that I've used PCA without telling you what PCA is and what it does, but I promise that I will. I want to show you the results first and then the concepts. But it would be a fair observation in the sense that, a fair point, in the sense that you should know what it's doing. It's important to know what you're doing. Okay, somebody posted the first screenshot. So because somebody posted the first screenshot, I'm also going to start doing it. So I will copy this. Or would you rather me wait for another minute?
Maybe just wait a couple of seconds. Okay, I think you can go ahead.
Okay, same thing. Color equals labels. And then let's look at what happens. Okay, and I will also add a color bar. Okay, so this does not look great because I'm doing something that is not very correct, which is I'm using, so that's actually a nice example of what I was saying earlier. I'm using categorical data. So this 0 to 9 is in fact categories, right? They are not really numbers because we are talking about the digit 0, the digit 1. So it's categorical data. And I'm using here a color bar that consider these as numbers from 0 to 9, and so has a continuous sequence of things, of colors. That's not the right way of doing it, but it does give us an idea of what's going on right here. Maybe it's a bit better if I choose a color map that is more suitable. I've chosen PLT set 3. So this one looks like this. This is still not good. Because I'm still using something that uses them as a sequence. It just has sharp changes from the data. But in the interest of time, I will do it anyway like this. But there should be better ways, which are associating to every category its own color. I think somebody maybe in the comments did that in the. But anyway, this is a coding exercise, and I don't really want to spend time on this right now. Okay, so somebody is commenting the fact that within 64 dimensions, 62 are negligible is amazing. Thanks for the comment. I think saying that 62 is negligible is not is a bit unfair. It's a bit unfair because, as you can see, there is a lot of overlap. So number 5, for example, overlaps with all the others. But if you told me that maybe among 64 dimensions, 40 are negligible, then yes, I would agree with you. You can compress the dimensionality to maybe 10 dimensions, and that would be enough to reproduce the data very well. But think about it. So far, I've talked about it in terms of projection to a subspace. So I've tried to adopt like a mathematical geometrical perspective. But you can also think about it in terms of information theory, if you're more familiar with it. So this image is really compressible in terms of information. And that's, the bitmap representation of the bitmap format is for each pixel you give a color, or 3, which is a number, or 3 colors if it's RGB, or 4 colors if it's RGBA. Okay, but think of JPEG compression. JPEG compression doesn't assign a color to each pixel. It summarizes various pixels by compressing. And you can do compression only when there are spurious dimensions. There is information that is not really needed. So you can compress by exploiting correlations. Okay, so I've talked about exploiting correlations right here. And that's when it's a good time to start talking about how PCA actually works and what it does. What happened? Oh my God. Sorry, my computer is doing things. All right. So dimensionality reduction. I should say that there are many ways of doing dimensionality reduction. And once again, the same as I've done for k-means, I've chosen a specific example of how to do dimensionality reduction, specific algorithm, PCA, which is the most common one. And I will explain this one just as an example. How does PCA work? So here's our image of a 0. And as I was saying earlier, there's going to be a strong correlation between these 2 pixels, right? They are likely to be of a similar color. On the other hand, this pixel here, which is usually white, and this pixel here are also going to be likely of the same color. Any neighboring pixels are likely to be of the same color. So this is redundancy. It's like you are likely to be repeating the same information on neighboring pixels from an information theory point of view. And you are on a smaller subspace on a geometric point of view. So I've got you the covariance matrix and pixels. So we have 1,700 something samples, and we have 64 features. So this is a 64 by 64 matrix, which I've plotted as color because it's a bit more intuitive. So you have the covariances between the pixels. Not that I cannot see questions now that I'm full screen. So if there are any urgent questions, please let me know. Some pixels are correlated, some pixels are anti-correlated, but in either way, we can exploit this. Now, to go a little bit into maths again, because I think you can take it, and if you don't understand it, that's okay. I will try to have a more intuitive view later. This is a symmetric and positive definite matrix. So it's always diagonalizable, and there is a space of eigenvectors of this matrix, which form a basis of our 64-dimensional space. So I'm going to diagonalize this matrix. There you go. It's now diagonal. So I've only done a linear coordinate transformation in our space. But I've done a special one. I've chosen it so that all the variables are now uncorrelated, statistically independent in a linear sense. So they are uncorrelated. The Pearson correlation, their covariance is 0, and they have different variances. So each of these new variables that we have is a linear combination of the previous ones, but this time they are not correlated to each other, and they have different variances. The ones with more variance have a lot of variability. And so this tells us that that their values describe and tell us a lot about the data set. There is more information in them. These ones have very little variance. If there's very little variance, there is little information that we can extract from them. So what we do is we take the eigenvectors as the directions that tell us this is the first principal component. This linear combination of variables is the first principal component, and is one principal component. And then we order the eigenvalues from largest to smallest. And the ones corresponding to larger eigenvalues have the larger variance. So those are the important features. So the ones with the largest eigenvalue is the eigenvector or combination of variables or dimension. That is the first principal component. The second one is the second principal component, until the last ones, which have very little importance. If you are extremely confused by all this, which is completely possible and fair, let's have a look at an example. So here we have a two-dimensional data set with two variables, x and y, which are correlated to each other. And it's natural that in any natural data set, there will be correlations. And you know, by nature, unless you've chosen it to really to be independent, typically there will be correlations in nature. So we have two dimensions, x and y, and we want to find the first principal component. We want to reduce dimensionality to one dimension. How do we do this? Finding the covariance matrix and diagonalizing it essentially means we find new variables that are uncorrelated, which is we find the ellipsoid of the covariance matrix. In this case, because this is a nice example of Gaussian variables, it's very easy to see it. And it's like this. So if I rotated this data set and I used x prime and y prime as axes, you will see that there is no correlation. So if I look into this direction here, x prime and y prime are not correlated, whereas x and y, of course, they are correlated. I can see that there's a nice line here. There's a nice linear correlation. But between these two, there is no correlation. Okay? So this is the new space. Now I choose the one with the highest variance. That's y prime. And I call it principal component or first principal component. And this one I call secondary component or second principal component. I hope it's clear. If it's not clear, I'm sure you will find maybe people that have done this with a nice animation, or you can ask in the questions and we'll talk about it. So does this always work? Of course not. It's a linear method. We are finding a linear subspace. That's a very strong assumption. Here's an example where it will fail terribly. You can see here that there are two nice variables to describe this. There are two very smart variables that we can use to describe this. Theta and r. So moving to polar coordinates is the right thing to do here. And also theta has a very large variability because it goes from 0 to 2 pi. So we have all the thetas. R probably is not the it has low variability, so probably is not the interesting one. It may be. This of course depends on the data. But the important thing is that r and theta here are uncorrelated, so they are definitely interesting in some sort. They are objectively interesting in some way. Okay, so. But PCA is never going to find them. If we start with the x and y Cartesian variables, PCA is never going to find out that there is a way of uncorrelating them. Because for PCA, these are already uncorrelated. There is no correlation between x and y. And yet, there is a much smarter thing to do, which is finding r and theta. But because the relation between them is nonlinear, they are not going to find it. Okay. Any questions? And then I'll give you some examples of more juicy examples of how this could be used. I don't see any questions.
I don't see any question either.
All right. I hope it doesn't mean that everybody is mind blown and very confused. So let me show you a very cool use of dimensionality reduction, which is already kind of old. This is PCA, so it's linear. Now imagine, I'm not showing the slide yet because I want some suspense. Imagine the DNA of a person, or even just a small set of genetic properties. It's a huge space. Our DNA is absolutely humongous, right? But the parts that actually vary from human to human are not so many. We are, I guess 99% and more of my DNA is the same as you guys' DNA. In fact, is even the same as any other mammal's DNA, a lot of it. So the dimensions that really show variability are very few. I'm not an expert in genetics and in population genetics, disclaimer. But there's this really nice work from Cavalli Sforza already in the 90s, where they did PCA on some kind of genetics data in Europe. They looked at the first principal component, and then they mapped the value of that axis of the principal component on the map of Europe. The result is this principal component is very high in the Middle East and very low in Scandinavia. Or you could say the opposite, right? Because in fact there's a sign equivalence, so you could swap it and choose the other direction and say that it's high here and low here. And this, on an historical anthropology point of view, is considered to be related to the spread of agriculture. So in the history of human populations. Because of course our DNA comes from the way we descended from each other in history. The second principal component, I haven't plotted it. It's high around here, so that has to do with Caucasian populations and stuff like that. But I really like the third one, so I plotted the third one. The third one really corresponds. The black area here really corresponds to the original Greek colonies. That's where Greeks first inhabited the Mediterranean, and it gets the farther away from Greece you go, the lower it becomes. So the magic of this of dimensionality reduction is that very often you find meaningful directions in your data by doing dimensionality reduction. If there are hidden patterns, you may find the hidden patterns if you are within the hypothesis. And then you can plot the fifth principal component. I haven't done it. Corresponds to the Basque country. And the Basques are a population which were kind of isolated for a long time. So that's also not surprising. So I find this really mind-blowing. I really love it. Then I'm a bit late. I will show you another example of things that we do today. So very modern, very contemporary. This is 2018 stuff. Here, 2018. This is very much not PCA, is very much not linear at all. So it's done using a tool called variational autoencoders. So it's deep learning, big neural networks. I'm going to tell you just for fun, for a moment, how an autoencoder works. It's a neural network that takes an image or whatever else as an input. Let's say it's an image, like in this case. And then it's trained to spit the same thing as an output. That's why it's called an autoencoder. It has to learn how to reproduce the same data. So why is it useful? The trick is that the middle part of the layer has to go through a bottleneck. The middle part of the network, of the model, has to go through a bottleneck. So the network is forced to encode the input into a lower dimensional space and then reproduce it again as a higher, as the original input. And in doing so, it discovers the very nonlinear embedding in the middle of the neural network. If you're not familiar with neural network, this may be very confusing. But the idea is that you automatically find a nonlinear embedding by doing very agnostic, very hands-off learning on a neural network. So this lets you do this kind of magic, because then in that nonlinear low dimensional subspace, embedding in the language of machine learning, you find directions like, or you can explicitly build directions like smiling versus frowning, eyes opening versus eye closing. The reason you find these is that these are variables that exist naturally in our datasets, in our pictures, and are independent of every other, right? You can open and close the eyes independently of the size of your nose or whether you have glasses or not. So automatically, the machine learning model disentangles these representations that are independent from each other and lets you find them. So once you found it, you can then feed an image like this one to the model, and then look at the embedding and change only that direction. You keep all the others the same, and then you change the direction that you know corresponds to smiling and frowning in one direction, and then decode, so go backwards and go back to the image space. And so you can have the same image changed into smiling, changed into frowning, changed into eyes open and eyes closed. So that's a cool application of sophisticated dimensionality reduction, much above PCA. Okay, two quick things. Let me go back to the notebook. Any questions, first of all? When there are no questions, I always get a little worried.
Oh, I think everybody is impressed by the examples.
Okay. Maybe I was also talking a bit too much. Okay, we've done this. So I have two more things to say. The first is, somebody was saying, I'm impressed that you can that I can describe this data set, which is 64 dimensional, just with 2 dimensions. Can we quantify exactly how much can we tell about this data set using only 2 dimensions? The answer is yes. Once the PCA model has been fitted, I can look into a thing called model dot, I forgot. PCA explained variance. Explained variance ratio. Okay, what are these two things? The whole data set has a certain amount of variance. Okay, you can assign this variance to the various dimensions. Let me go back to the slides for a second. So my MacBook decided that when I press play, it will also open iTunes, which is ridiculous. Okay, so there is a certain amount of variance, of total variance. Some of it is in this dimension, and some of it is in this dimension. Okay, so we can disentangle those. And show and say that one direction has more variance than the other direction. In this case, you don't see it because these 2 directions more or less have the same variance, kind of. Let me do the transformation without reducing the dimensionality. So we move into the space of eigenvectors. We rotate the model, if you wish. We rotate the data set, if you wish, not the model, sorry. But without reducing the dimensionality. So to do that, we define another model, also PCA, and n dimensions equals 64, which is in fact default. The default is keep the same number of dimensions. Okay, and then we fit it to the data. Oops. N components. Okay, and now I do model explain variance ratio. So this tells you the fraction of variance that is captured by the first principal component, as opposed to the fraction of variance that is captured by all the others. To understand what's going on, let's plot it as dots. Here you go. So the first principal component alone captures 15% of the variance of the data, which means that if you only had that component, you would have lost information about the variability, the differences, the different properties. You would have lost everything but 15% of this information. The second one has 13, 14% of it. The third one, 12%, and so on. So there are a few very important ones, 4 or 5. And then until 20, they are somewhat important. After 20 or 30, they are essentially irrelevant dimensions. Perhaps we can do a cumulative sum from numpy import CumSum. So if I do CumSum of this, so that means we accumulate. So we do 15, and then instead of displaying 14, I display 15 plus 14. Okay. So this shows that if we had 10 dimensions, 80% of the internal variability of the dataset would be captured. So 80% about the information about the differences between digits would be captured. That's probably more than enough to classify. So you're compressing. So that's the one thing that I wanted to say. The second thing, which we can treat as an exercise, is so far I've shown you only one dimensionality reduction algorithm. Let's try a different one. Let's try one that is nonlinear and is much more powerful. This one is called from scikit-learn dot manifold import tsni. So this is a mathematically sophisticated algorithm. I honestly don't know how to explain how it works. I will pause and let you try it, and let me know how the results go, and if you find it better or worse. I will wait for 2-3 minutes, and the syntax is always the same. And in the meantime, of course, if there are questions, let me know.
Okay, I should probably continue. I just wanted to say, I hope you can still hear me. Everything is fine. And so somebody showed the results with Tisni, and it looks really great. I'm just gonna show it from the Slack itself. I've lost it. Sorry. So somebody posted this, which I think looks great. As you can see, because it's nonlinear and it can do something much more, then it works way better. One word of warning: you may be thinking that it would be very easy to do clustering on this, and so it would be a great thing to do. They say, those that know the theoretical aspects of Tisni say that this is not a theoretically sound thing to do, because Tisni can distort features in a way that makes it not really suitable for clustering. Now, of course, in this specific example, it would have worked amazingly well. So we could have done that and it would have definitely worked. But we can't always do that. Okay. Okay. Any questions about? So I'm not going to code it because Tisni is a bit slow to converge. So I don't wanna waste too much time. If there are no more questions, I will proceed to the second part of this tutorial. And this part is about classification. Classification is the most, okay, there is a question. Feel free to write, I will pick it up later. Classification is possibly the most common task for learning machine learning. In fact, I did not, sadly, I did not spend so much time on classification because I was thinking that in the deep learning tutorial tomorrow, there was going to be a lot of classification. So I thought, okay, I will keep it a bit shorter in this side. Unfortunately, there is no deep learning tutorial tomorrow. However, now you will know what classification is, and you will be able to use it anyway. To go back for a second, why are there, somebody's asking, why are some clusters different in several plots? This is again a matter of randomness and of how the algorithms, either the algorithm itself or the initialization of the algorithm, so the initial position can be random. And so the way it converges is always slightly different. If you want consistent results, you can freeze the random seed and it will be consistent. Or they can be the same clusters but move to different positions, and that's because maybe the algorithm, because it's unsupervised, things are invariant. You could, for like if the X and Y can be swapped, the sign can be swapped, and there is, geometrically speaking, there's no difference. Only the mathematical description changes, but geometrically you're still there. So so this is always invariant. Okay, so let's go into classification. I'm going to now use the digits dataset for what is meant to be used, which is, in fact, a classification task. So here we've played with it for dimensionality reduction, which is not even the best dataset for this. Somebody in the comments was mentioning we could use the faces dataset. So you can really do pretty cool things already, even on pictures of faces, and show that, for example, the typical variability of a face is in a certain direction. like again, like eyes closed, eyes open, or size of nose, and those are, you could call eigenfaces, because they are the variation, independent variation directions of faces dataset. So that's a nice exercise, actually. You can find the faces dataset and experiment with it with PCA. Okay, so classification. We are going to use the digits dataset for the reason it was made, which is we go from the image of the scan to what digit is in it. Why is this interesting? I mean, this is the whole point, right? This kind of task is one of the early computer vision tasks, which was used for things like, a common example is postcode recognition. People write letters by hand, write the address, and I want to sort letters. Of course, the post office has to sort thousands and thousands of letters every day. So you want to do it through a machine, but they are handwritten letters, which are not so easy to read because everybody writes in a different way. So at least the postcode, you can read the numbers. And then, of course, today we can also easily read the letters and so on. Or it could be on checks. Now your bank sometimes allows you to deposit a check by taking a picture of it. And then it gets scanned and read automatically by an OCR, optical character recognition. So optical character recognition is based on this kind of models. And yeah, so what we want is really recognize these characters for all the applications of this stuff. So what models do we use? Usually vision tasks like character recognition, image recognition, and so on. These days, they are solved with neural networks. Because they really, so in this domain, they really are better than anything else by far. However, there are also some easy, smaller, easier classification tools, which can be used on smaller dataset. And this is a 64-dimensional dataset, which is not very big, so we can use something like that. Note that, speaking of this, using a stronger, more powerful model is not always better. In fact, it can be a problem. So if I used on this dataset, if I used a super huge neural network or a very sophisticated large model on a small dataset, which has only 1,700 examples and 64 dimensions, I'm going to wildly overfit. So then the model is going to be so powerful that it will learn every digit by heart and have it in memory, instead of being forced to figure out the meaning of things, the meaning of pixels. So then you get overfitting, and the model doesn't generalize. So as soon as it sees an image which is different from the ones that it has seen, so for example, the test set or the real world, it will not know how to deal with it. More about this in Claudia's workshop this afternoon. So to defend ourselves from this, we have to use always the smallest model that works. And we also do the training and testing split. So for the first time now, I'm actually going to do this because I think the time has come. It's important. So we use we divide randomly. So we shuffle the dataset randomly, and we take maybe 70%, 80% of the data as training set, and 20% of the data as test set. To do this, there's a nice function that does it for us in scikit-learn, and that's in the 6th section of scikit-learn, the one about model selection. Import train test split. Okay, data train, data test, labels train, and labels test equals train test split of our original data and our original labels. Does it work? It works. So now data train contains only 1,300 data, and data test contains 450. which is probably 80%. Maybe let's make it 70%, just to make the training a little more difficult. Test size equals 0.3, so we have 30%. Okay, so it's a little bigger. All right, now I can reveal what model I'm going to use for classification. I will use a model called support vector machine. If we have time, perhaps I'm going to try showing you a little bit of neural networks, since there is no tutorial tomorrow. So the support vector classifier from scikit-learn.svm, support vector machine, we import SVC, which means support vector machine classifier. We know nothing about this model. So far, I've first shown you the result and then explained how it worked. But now I'm going to first explain a little bit about how it works very briefly. Why? Because suppose that we want to use this, then in Python notebooks, you can type SVC ? And it gives you the documentation, right? So that's the documentation. Suppose that we don't know anything about it and we want to use it. We have no clue about what is all this stuff. What is C, kernel, degree, gamma, coef0, shrinking, toll, cache size, class weight? And we can look at the documentation, and it doesn't really tell us that much. I mean, it assumes that you know a little bit about what it is. What's the kernel? Specifies the kernel type used in the algorithm. It must be used of linear, poly, RBF, sigmoid. What are these things? Regularization parameter. Degree of the polynomial, gamma. Okay, so this is the other important reason why we need to know a little bit about our models. The first one is we need to be in the right assumptions. We need to be using them for the right thing that they were made of. And the second one is we need to choose the hyperparameters. We need to know how to choose the hyperparameters. We need to understand what they are. So let me again bring up for the umpteenth time my slides and talk a little bit about this. So this time, support vector machines are they are a little less. They are a bit more complicated to understand. So I'm going to give you an intuitive understanding only. Also because I'm not an expert. I don't use them very much. Usually I use neural networks. In fact, I'm a neural networks person, and I've also studied some neuroscience. But I explicitly avoided talking about neural networks because of the deep learning workshop. Okay, so support vector machine. We are doing classification. So we have two sets of data, and these data are labeled. So we already know which ones are green and which ones are orange. What we want to do is to find the boundary between them, think in a very abstract sense, not in 2 dimensions, think in 100, 1,000 non-linear dimensions, whatever. We have to kind of separate between them and decide where the decision boundary between them is. Once we have this decision boundary, then we say everything to the left should be of class 0, and everything to the right should be class 1. So if we have new data points, the ones in the test set, we immediately know this belongs to this class, this belongs to the other class. Now, so SVM usually separates between 2 classes, is made for 2 classes, but you can extend it by doing pair by pair. You can extend it to any number of classes. Okay, so we are trying to find the line between them, which is a hyperplane if you're working in very high dimensions. How do we choose? There are many ways of choosing the hyperplane. Like I could have chosen a vertical line here using only one variable, and this would have correctly split the 2. I could have chosen a line very near to this data set, and everything else is orange. I could have chosen a line very near to this data set so that everything else is green. There are many ways of doing this. The point of SVM is finding the maximum margin classifier. The one that is equidistant, that leaves the same margin on both sides between the separation line and the so-called support vector. The support vector is the representative sample of the other data, of the two datasets, of the two families, which is the one that is nearest to the boundary normally. However, if we really use the ones that is nearest to the boundary, we would have a big problem whenever there is an outlier. So in fact, there are algorithms that do it in a less noise-sensitive way. So that's the kind of the intuitive view of what this is doing. It's finding the classifier of maximum margin between the two by an optimization process, as always. However, if you guys have an eye for details, some of you may have already noticed that if I do it like this, this is linear stuff. I may have a 1,000-dimensional data set, but if I have a data set that looks like this, there is no way to separate with a single line, separate the green dots from the orange dots. And this is actually very typical. I mean, it happens a lot that you have non-linearly separable data sets. Earlier, I was mentioning that there was a sort of so-called AI winter in the 70s. And one of they say that it's not really true that it was because of that. There were multiple reasons, but they say also that one of the reasons is that the perceptron, which was the model that was most widely used at the time, could not do separation of non-linearly separable data sets. And to do so, they had to have multiple layers of the neural network that they were using at the time had to have multiple layers. But when they had multiple layers, they didn't know how to train it. They didn't know how to optimize the parameters. And then this was solved by inventing backpropagation later. This is kind of an aside. In support vector machines, how do we solve this problem? By a trick. The trick is mathematically is a bit more complicated, but effectively what it does is here we have a one-dimensional data set, and that's the axis. What we do is we add another dimension. The other dimension we add is a non-linear function of the previous dimension. For example, here I've put them in a sort of parabola. I've kind of squared somewhat this value and obtained this value here. So now I haven't done it, I mean, this I did by hand. I haven't done it very well. But you can see that now they are linearly separable. These three are there is this line that is a possible separation. What actually happens behind the scenes is mathematically more interesting and more complicated, a lot more efficient than actually generating new dimensions for all the data. But sort of the idea, the geometrical intuitive idea is that this is what effectively happens. You have additional nonlinear, additional dimensions that are non-linearly dependent on the previous ones, so that the data set becomes linearly separable. Okay, if there are questions, please let me know. I think maybe there is something. No. Okay, so now let's do this. By using scikit-learn as always. So now we know what these mean a little more. The kernel is the kind of function that we want to use. It could be a linear function, then we are not doing much. It can be a polynomial function, and in this case, the degree, we can decide the degree. It can be a radial basis function, and that's the default, and this is what we're going to do. The radial basis function is essentially an exponential decay. And then gamma is by how much we decay. Among the other, so there are a lot of other hyperparameters. Among the other important ones, I would mention C. C is a regularization parameter. What is a regularization parameter? When you have a strong regularization, you are trying to put constraints on the model. you're trying to force it in a cage in a way that makes it a little weaker, but also makes it generalize better. So that's what I was mentioning earlier, that you don't, if you have a model that is too powerful, it will overfit and it will not generalize. So this is one of the reasons why we need the regularization. Again, it's a hyperparameter that needs to be chosen by model selection methods and so on. It's not obvious, but I just wanted to explain the term regularization. We don't really have time to go into it, but it's an important concept, so I wanted you to have heard of it. So, okay, so let's define our model equals SVC. So that's our support vector classifier. And for example, let's choose the parameter gamma to be equal to 0.01. I put it there so that later we can play with it and see what happens when we change it. Okay, so we move on to training. Model.fit. The syntax, again, is always the same. This time we need the training data. And because it's supervised, for the first time today, we are doing a supervised algorithm, then we need the labels as well as a second input to the model. Okay, and let's let it, okay, it fits very quickly. It's a fast algorithm. Okay, so now we have the model and we want to use it. First we've fitted, now we want to predict. So first we predict on the training set. So we want to show that at least on the training set it works. And then we also want it on the test set. Sorry, we should assign this to prediction, train, and prediction. But in the meantime, you've seen here what the output of the prediction is. What are these? They are guesses. They are guesses of the first image contains a 4, the second image contains a 3, and so on. All right. How do we show that this has worked properly? Let's start with one image. So let's show an image. We've done it here, so I'm going to copy this. Okay, but this time I want to show specifically data test. I want to show a member of the test set. For example, the first one, 0. How does it look like? It seems to be a 4. And so let's print the expected label. That's the one given by that was already present in the training set. And that we get from labels test 0, because we use the first one. And then we also print the model predicted. What did it predict? Prediction test 0. It worked, hooray. Okay, so it reliably told us. So this is what was given to us with the data. It was the label that was done by hand by someone who made the data set. And this is after training, the model responded by being able to actually tell that this is a 4. So it worked. Of course, looking at all the samples one by one is not the right way of evaluating if the model worked. So how do we do it? We need to define measures of merit, figures of merit, measures that tell us whether the model worked well or not. The most obvious one is we look at in how many cases did these two coincide. Okay, how many cases did it get it right and how many cases did it get it wrong? Okay, so the way I do this is if I do labels test equals predicted test. So these are prediction. These are compared one by one, and it gives us true whenever they coincide and false when they don't coincide. If I compute the mean of this, because true is treated as a 1 and false is treated as a 0, this gives us exactly the fraction of true answers. And I get 0.99. How does that sound? It's nice, no? And a warning. This is a nice balanced data set. So we have the same, roughly the same number of four-digit images, the same number of ones, of twos, of threes, of fives, and so on. Okay, so this is called a balanced data set because every class has roughly the same number of samples. But sometimes it's not like that. I may have very few, if you're classifying something, I may have very few positive cases compared to negative cases, for example. In this case, the accuracy is not going to be reliable because say that you have a data set of sick people versus healthy people, okay? So you're doing a COVID test, for example. 99% of people don't have COVID. And so in your data set, you will have results for 99 healthy people and 1 non-healthy person. If your model simply says, I'm just gonna say everybody's healthy. 100% of cases, whatever the person is, whatever the test is, I'm just not going to look at the data at all. I'm just gonna say the result is healthy. You look at the accuracy is 99% because 99% of the test set are healthy people. So in 99% of cases, it gets it right. So the accuracy is not the right way of doing this. And Claudia in the afternoon is going to talk about the other figures of merit, or if you've studied statistics, you will have heard of working with true positives, true negatives, precision, recall, specificity, sensitivity, and so on, F-scores, all these kind of things. Okay, so we have time. I would like to ask you to play with the hyperparameters of SVC and see if you manage to break it to make the result bad. Play with the hyperparameters and look at the corresponding accuracy. Can you get it to not work? Okay, so that's the exercise. I'm going to stop for 5 minutes so you have time to play with it, and in the meantime, feel free to ask questions. Okay. People are starting to play with it. And they say that if you make gamma very, very small or very, very large, it stops working. Okay. It still works pretty well with this gamma. Okay, like this, it doesn't work. Of course, it will never go below roughly 10%, okay? Because 10% is chance. So unless you're doing something really, really wrong, the model will not behave worse than chance. And because we have 10 classes, chance is 10%. So yeah, whether it overfits or underfits, I don't know, it depends. Well, what the parameter gamma does, it kind of makes it so that if gamma is very small, the support vector classifier doesn't look around very much. Every data point is isolated by itself. It's a bit difficult to explain intuitively. And if gamma is large, like 10, what happens? Yeah, also very bad. Okay, so this was the example. I hope this teaches you, okay, the way you select hyperparameters. You have a test set and see what happens. See how your generalization properties are like. And this is also sometimes ironically called optimization by grad student, which means instead of having you optimize, the computer optimizes the parameters. For optimizing the hyperparameters, you get a grad student and you ask them to try all the possible combinations of hyperparameters until it works, which is not, of course, is not a very good thing to do. So if you really do that, if you try a lot of hyperparameters, it's important to have another test set. So you would have, they would be called training set, validation set, and then test set. Because the risk is that your test set here influences your decision on the hyperparameters. So first you decide the hyperparameters on the validation set, and then when you're chosen, in the end, you really use the training set. Sorry, the test set, the proper test set. We have another 5 minutes. While you're playing, I'm also going to show you another useful thing, which is matrix, import plot confusion matrix. And then we do plot confusion matrix of, we have to pass the model, the test data, and the test labels. And it shows us this. So by this, you can tell not only what succeeds and what fails, but how it fails. So for true label 9, for example, so samples in the datasets which contain an actual true 9, in 60 cases, we get 9. So we get the correct result 9. In one case, we get a prediction of 5, so that we got it wrong. So this is how you read it. It's a confusion matrix. You can also read it the other way around. So you know that if the result was 5, what are the chances that it was truly a 5? Well, in 46 cases, it was a 5. In one case, it got it wrong, it was a 1. And in another case, it was a 9. So that's how you read a confusion matrix. Of course, there is only one way of getting things right, and there are many ways of getting things wrong. So the confusion matrix is particularly interesting when things go wrong, and then you can use it as a diagnosing tool. So for example, let's again make this gamma very bad and see how the confusion matrix looks like. Okay, so what happens when your gamma is super bad is the model, regardless of the input, the model answers 5. That's why it doesn't work. That's why the accuracy is 8.5%, because 8.5% of the data in the test set is 5s. So in that case, it randomly gets it right. That's these 46 cases. I think we have 3 minutes left, right? So ask all the questions you want. If you want to experiment with other models, you could try things called k-nearest neighbors and multi-layer perceptron classifier. I'm not sure it's called like this in scikit-learn. Let me look for it. Yes. Okay, so one example you could try if you want to try different models. It's called scikit-learn.neuralnetwork.mlp classifier. That's a multi-layer perceptron. So that's the easiest, simplest form of neural network, which is the one that was already popular in the 70s. It's a good starting point if you want to get into neural networks. So I recommend trying it out and also trying to really understand what it's doing. The other one you could try is called k-nearest neighbors. That's a very, very simple model. Okay, so to answer questions, somebody is asking, can confusion matrix be different in different runs? It can be different for 2 reasons. If you select the test set randomly every time, it will be different, but you should not do that. The test set should always be the same. You should select it at the beginning and keep it. So that's one source of randomness. The other source of randomness could be if the model itself is random. Usually it's not like that. Once you've trained it, usually models are not random, but who knows, there may be random models. So you should get the same confusion matrix if you haven't retrained the model. If you have retrained the model, then the model may be slightly different, as we've seen before. So then you would get a different result. Sorry. Okay, another question. Okay, somebody's saying that somebody's complimenting me, so thank you. Somebody's asking, I've used TensorFlow a little bit from neural networks. What are your thoughts on using TensorFlow versus scikit-learn? So as I said at the very beginning, scikit-learn is not really for neural networks. The only neural network that scikit-learn contains is this MLP classifier and the corresponding MLP regressor. But these are very small networks. They're very small neural networks, which are used for small data sets. And for small data sets, maybe SVC is actually better. If you want to use deep neural networks, deep learning, then you should not use scikit-learn. Scikit-learn is not capable of that. Doesn't do, for example, convolutional networks for vision, but any kind of deep network, you should not use scikit-learn. You should use either TensorFlow, which, to be honest, I don't use usually. I use PyTorch instead. So they are equivalent. They are sort of rivals. PyTorch was built by Facebook Research originally, but now is open source, and I love it personally. I find it very intuitive, very easy to use, and super powerful. TensorFlow is written and maintained by Google. It's also extremely powerful. I think it got a bit simpler to use in recent years compared to the very beginning, but I still find it a bit more cumbersome, to be honest. They both have support for GPU. Because the moment you start training a very big neural network with millions of parameters, you will need to compute on the GPU. Otherwise, it takes the age of the universe. I hope this answers it. There are so many other things that I would have liked to tell you about neural networks, about all sorts of things, but there is no time. I'm still here for questions for a few minutes if you like, and otherwise, thanks for coming and enjoy your lunch.
Okay, I don't see any other question. Thank you again very much, Martino, for the lecture. As someone said in the chat, I think it was a great balance between the lecture, the interactivity, the exercises. So, and I know it's not an easy exercise to do that.
Speaking of this, I would like to ask people to give me feedback on the way I've done it. So I have a link for that if you don't mind.
Sure, no problem. You can find it in the Slack.
I have to figure out where I put it. There it is. So I will copy it in the Slack.
Yeah.
And so it works. You should copy paste it. It's a single link. Slack is separating it because it has spaces, but you should copy paste it because it's actually a single link. The way it works is you can leave one positive thing and one thing to improve, one negative thing. Please don't choose one. Do both. There's one question that says, in SVC, data either above or below the margin, so there's no more probabilistic explanation. Yes, so in fact, the way is actually implemented is more is less sensitive to noise, so it allows for outliers. But in the intuitive explanation that I gave was the hard version where that doesn't happen. Okay, then. Thank you, everybody. And see you this afternoon with Claudia at 2, right?
Yeah, exactly. We resume at 2 p.m. with Claudia. Thank you very much again.
Thank you.